Today's visualization explores the Aizawa Attractor, a remarkable form of spherical chaos. Although it looks like a glowing, breathing shell, everything you see is the path of a single point moving according to three nonlinear differential equations. The attractor was introduced in the late 1980s by Hiroshi Aizawa, who discovered that with the right parameters, chaotic motion collapses into a compact spherical structure instead of spreading outward like the Lorentz system. In the first scene, we witness the birth of the sphere. The trajectory begins loosely, spiraling around an invisible core. Each loop refines the shape, gradually forming the curved outer shell that defines the attractor. The second scene shows x of t as a chaotic time series. Sharp peaks and dips flash across the screen, revealing how violently the system swings horizontally. The irregular spacing of these spikes is a hallmark of deterministic chaos. Next, the ZT graph enters, displaying a smoother, wave-like rhythm. These repeating arcs reflect the vertical breathing of the attractor, rising and falling as nonlinear feedback forces push the particle inward and outward. Small ripples along each wave hint at the complexity inside the equations. The phase plot of x versus y presents a top-down perspective. Spiraling loops drift and overlap, creating a circular maze of motion. This view highlights the rotational heartbeat of the system, where each revolution is similar but never identical. In the 3D isometric scene, depth becomes visible. The path folds around two main channels, twisting through a central column before sweeping outward again. This is where the attractor's layered structure becomes easiest to appreciate. Finally, the Aizawa sphere appears in full form. The curve wraps tightly around a spherical boundary, never repeating, never escaping, yet always staying beautifully contained. The subtle pulsing applied in the engine makes the structure feel alive, emphasizing the natural elegance hidden inside the equations. Subscribe for more CM2A explorations.